Okay, let's continue. I would say this is part 7, and we will get into introduction to thermodynamics. But before we get in there, we need to continue from where we left off. Now, last minute we did on part 6. We introduced the latent heats, right? 2 latent heats, right? One is the heat or the thermal energy required to change the physical state from solid to liquid, right? Another one is the heat or the energy required to change the physical state for, let's say we use water right here, or any substances, from liquid to gas. So for water, we talk about it, right? The water, H2O, right? It's physical state change between solid and liquid water is at 0 degree. It's a solid ice and icy water. It requires positive, negative, plus minus 80 calories per gram. We already discussed there's no symbol for temperature because temperature doesn't change. That's the temperature we call freezing point or melting point for water, right? 0 degree or 32 degree Fahrenheit. Either way, use a different kind of scale. But it requires 80 calories. But there is a sign problem here. Why this value has to have plus minus sign? Well, because you have two coexisting physical state. It can go either way. If you absorb the heat, and then you can melt ice into liquid water. If you lose the heat from the liquid water, icy water, then the icy water can be frozen into solid ice. They both process at exactly 0 degrees Celsius temperature. So one is absorbing heat, one evolves heat or gives away the heat. That's two totally opposite situation, opposite process. Right? So that's why we involve energy either adding to the ice to melt ice, or the icy water has to give away its heat, give away to be frozen into ice. So you gain some heat for ice to be melted. You gain something, of course, use add because you positively add some value to it. But if you give away, like you lose some heat, and then you give a value in the term of heat, it's going to be negative. Now, there's something we have not yet reached, but we will discuss today in detail in just 30 minutes about very beginning the concept of thermodynamics, right? Now, the second situation is at 100 degrees Celsius. At that temperature, liquid water boils to steam. So there's two physical states coexist. One is liquid water, boiling water. Another one is a steam. It's a gas. So what kind of amount of energy involved? Is it positive, negative, or plus minus 539, something round up to 540 calories per gram of boiling water convert to 1 gram of steam. All right, that is the coexistence of liquid and gas at 100 degrees. That's called a boiling point, or simplified as a BP. Then first case we call MP. So sometimes you see literature says this is an MP. MP. And this is going to be called BP. Boiling point and the melting point, right? Temperature, right? So at 100 degrees, these two states, physical state, coexist, but they are able to convert between each other if you have energy involved the opposite direction. So in this case, that's why we have positive and the negative. When we have a positive means the boiling water absorbs this huge, that's a huge amount, 540 calories, and into it, and then get all these molecules of water, H2O molecule get loose from the molecular interact, intermolecular force, and then get loose and become separated molecules into the air as steam. Or those steam can be lose some heat losing some heat, and then give away some heat, and then being condensed back to liquid water. Now you know that is very hot, right? So this situation, that's why they have plus minus sign for both. So you have to be very careful and clear on which one it goes, which physical state convert to which physical state, not vice versa, because there's a sign, plus minus sign involved. Very, very particular. It cannot be reversed, or you got wrong answer, right? Now let's conclude. This whole process, I put these into a table. I try to make a table and legible and as neat as possible. Here we go. I call it the table. What? Table for latent heats. Data on physical state change of water. Now, I did not put a physical state behind it in parentheses because it can involve solid, liquid, and gas. I'm just simplified as H2O. All right. I don't call it water because you talk water, you basically meant it's liquid, right? If you talk ice, it's going to be solid, or you talk about steam, that's a layman term, right? So we understand that. So we try to avoid that confusion. Now, the first part of my temperature. So at 0 degree, then the physical state for what? For the water is going to be coexist between the solid and liquid, right? Ice and icy water. And the enthalpy, now that is term brand new. You've never heard of it. Now, enthalpy means the heat. The heat in the process involved the process. So, because it's representing heat, so use H as a symbol for enthalpy. And the delta, of course, changed. The enthalpy changed. So, for the water as a system, now we're going to talk about a system, the term system, in the near future today. And then, in 30 minutes, part 7, and then the delta H means the enthalpy change of melting. Well, you talk about you want to melt ice, you need absorbed heat. You know that. So the ice cube, I said in part 6, if you have an ice cube in your palm and you wait long enough, it will melt. It will melt into what? A pool of icy water in your hand, in your palm, and then your palm, the center of your palm, under the ice or the icy water, you feel cold. Why you feel cold? Because your palm, your body, part of your body, give away part of your body heat into the ice. So the ice absorb into it and then get loose of the H2O molecule in the crystalline structure and become melt into liquid water. We talked about this already. So I just repeat for you, right? So that is process require energy. If it's require energy, we use endothermic. That's the term you learned a long time ago in middle school, high school. But you probably did not realize what is the real definition or it means what, right? So here we understand. If it's endothermic, the solid water absorbs what? Heat. I did not put down there, I just put heat. Absorbs, right? The opposite, to the contrary, if the liquid water, right, freezes back, icy water freezes back into ice, which should go the arrow this way, instead of to the right, it goes to the left. Look, we have a double arrow, means what? This process is reversible. That's a physical change process. It is not chemical because H2O does not change its composition. That's called chemical change and the physical change difference, right? The difference between physical change and chemical change is the composition involvement. If there's no composition change, that will be a physical change. So in the physical change, it's a reversible conversion. So when you freeze the liquid water, which is icy water, back to ice, the amount of heat absorbed from your palm will give away in other form into space, right? Emission and into space. And then icy water will be frozen back to ice. In this case, the value of the enthalpy, the heat, right, enthalpy, is going to be a negative value because for the water, H2O, as an entity, is to give away the heat and then itself getting frozen. So it's an exothermic process. So liquid water evolves. Evolves, I think, is the term gives away, right? Gives off. So that's the situation. Now, the second case is the 100-degree temperatures, higher temperature. Of course, ice already melts 100 degree prior, right? Prior. And so at the 100 degree liquid water boiling, that's called a boiling point, right? Boiling point, the BP, and then liquid water boils into hot steam, so it becomes gas. So, but these two physical states, they coexist at the same time, right? If I said last time for ice melt, you put a thermometer in there and pour water, icy water, temperature will be 0 degree, and touch the ice. You know, use a good thermometer, the mercury thermometer, and then you will find the temperature doesn't change. The column of mercury inside the tube, it doesn't move. It's still 0. In other words, at 0 degree, the solid ice and liquid water, icy water, they coexist. Temperature is exactly the same, but physical state change from liquid solid back to liquid, or liquid back to solid, right? The same token for liquid boiling water and the gas at a 100 degree, they coexist as well. So, but the process is opposite. There are two processes involved in physical change. One is when the water, H2O, liquid, absorbs heat, right? How much you probably have ever tried, right? At least once boiling water, right? If you never did, go home, try it. You boil water, you have to turn on the gas stove or light up, and then the gas, the burning, and underneath, and then the water on top of the kettle start boiling, right? At 100 degrees, goes up, upside down, turn over. So that's boiling. You need to put energy into it. Everybody understands that. So you get evaporation, right? For the water, liquid water, evaporate into gas. So the enthalpy of evaporation, right, is going to be the positive value absorbed by the liquid water, right? It requires 540 calories per gram water, per milliliter of water. We already talked about water has a unique density. It's 1 gram per milliliter. We already did it in the couple parts 5 or part 6. We already mentioned that. So if you absorb heat, right? Water absorb heat to be boiled into steam is going to be an endothermic process, and the liquid water absorbs heat. To the contrary, to the opposite, right? Even they are coexist, and then the heat can be given off from the steam, and then the steam will recondense back to liquid water. That's also at 100 degrees. But that process will release how much? Release exactly the same amount of 540 calories per gram of steam. Will lose 540 calories per gram of steam, and that steam will come back and then condensed back to liquid water, which is at 100 degrees, still boiling, right? So that's the same. Now, why the value is exactly the same? One is positive, one is that. We already talked about. In this case, it's called an exothermic because steam gives away the heat, 540 calories per gram of a steam, and then so that the steam can go back, condense back to liquid water. So it's a giveaway. So why the same? Well, try to think why same. Because the law of conservation of energy. Now we already learned that, and that is another example for you to understand the amount of energy cannot be what? Destroyed or created, right? But converted and stored. That's one part of the process. In time, in time we learned the conservation law of energy, right? So, and also we sometimes call it the first law of thermodynamics. Now, in order to understand the whole process, we try to understand, now you should understand a little better why we call endothermic, take in, exothermic, give off, but by who? Right, by who? Here we are clear, it's by the water, but at the different stage, different process, by the water, or by the ice, or by the steam, or by the boiling water. So you have to be clear which one we talk about, the entity, why we have to be, because we have to understand from which state to which state they're going to different physical state. We call them as a substances is a totally different thing. Water or ice or steam, right? So there's different terms to describe different physical state of the same substance we call H2O, right? So now it's time for we to transform this process, if we understand, into a little deeper introduction of thermodynamics, or sometimes we call thermochemistry. Alright, that's the next part. Let's erase the board, and then we keep on going. Another 15 minutes, we're going to get into introduction of thermodynamics. Alright? Thermodynamics. Now, when we talk about a previous example about endothermic and exothermic, we use water, right? Now, water is one of the most common substances we can live without, right? And it's a small molecule, H2O, right? And it's polar. We all know that it's a good solvent. Can wash away a lot of dirts, right? Polar dirts. Now, there are millions and millions of substances, right? Water is a simple one. I would like to use it as an example because everybody knows it. And then, in this particular case, we talk about endothermic or exothermic process for the substances to absorb or give off the heat. And we already mentioned the heat, the value could be positive or negative. Why? Because there's a direction where the heat goes or where the heat comes, right? So, goes to where? Goes to who? Come from where? Come to who, right? So we need to know this. So in order to understand, we need to introduce the concept, right, in the thermodynamics, the beginning, in the introduction of thermodynamics. So we have to divide our universe into two separate entities, all right? The first one is the one we call system. What is system? In thermodynamics, or at this point we may call it thermochemistry. It doesn't matter, but it's similar. Thermochemistry involves heat, right? In order to find or study the heat involved or the energy involvement of the substance during a process, right? We interest. And then we have to define the vessel and its contents of our interest as a isolated system we call system entity, or what we call system. So what is system? System is the contents of substances of our interest and its vessel, the container, all right? Now, define as, so example can be in chemistry, right? A table salt solution, what's it called? Saline solution, correct? Saline solution, right? Let's say 100 milliliter saline solution in a 500 milliliter beaker, a glass beaker. So that is, this whole thing is called a system, right? Or another more general, everybody would be able to apply, right? The wax coffee cup with its lid, not a lid, with its lid, right? And 500 milliliter of hot coffee, right? Now, the hot coffee could be black coffee, could be creamy sugar added coffee, but that's so this is what we interest the coffee, the energy involved in coffee or energy involved with this salt solution, but the energy also will be affected a little bit by the beaker. So it's kind of a thin wall container, either the wax cup or the beaker, glass beaker, we have to include that vessel contain the item or substance of our interest. So that is called a system. All right. Then beyond the system, another entity in the universe. What do we call? Then the second one we call surroundings. Now, this term, you have to be careful. It has an S down there. Alright, but it does not necessarily mean it's a plural, could be singular. Alright, depends on the situation, you know. But normally we think it's a plural when you use this term. I think so. And but then the surrounding. What is surrounding? What do we define as surroundings? Right, surroundings. It's not surrounding like a stereo system surrounding sound. It is systems. Got S. Very picky. Science. All right. One word make a heck of a difference. All right. Surroundings. What is surrounding? Surroundings means what? Right. Beyond the system. Beyond the system, everything else. So outside the cup of coffee or the glass beaker, everything else. How big that entity would be? So big. If you do not care, you can include your house, your dining table, or the coffee shop, right? Or your lab with the beaker you're doing at chemistry lab, right? Or you drinking coffee at a coffee shop. What's it called? What do you call it? Starbucks, right? Starbucks, you know, the table and the coffee shop, and beyond the coffee shop, that block of street, all right? And then that is the city, and then you can go bigger to the county and the states and the country and the continents, the whole earth, and go out to the moon, even to Pluto, out of the solar system, and the entire universe, even multiverse. The whole thing is considered part of the surroundings. Now that's how big it is. But we are not able to reach that far. So most cases we consider surroundings is just beyond the scope of the system we consider as a surroundings. Now we are able to study and deal with the energy situation, either absorb in or give off to. Which direction? Go to surroundings, or surrounding give heat into the systems, or vice versa. Because we limited our scope, the study, the field, the size of the region, or the size of system and surrounding. Now we are able to deal with the energy change involvement. So that's the surroundings, all right? So surroundings. Then if we understand that, then we are able to continue. We talk about types of systems. Now we have to. Types of systems. Now how many types of systems in thermodynamics study? Types of system, there are 3 of them. Right? Number 1 system is what? It's open system. We call open system. Right? Open system is what? Open system is a system, the energy can be transferred between the system, which is this one, open system, right? The vessel of the item you're interested, system, and the surroundings freely. That's called open system. Now, is this system good enough for us to study the energy involvement? You say yes or you say no. You probably say yes, but I'll say no. Because why? Because too much involved, right? The energy can be transferred freely, and then the second term, the mass of the system and that of the surroundings also can be exchanged, no problem. Now, because both the energy can be exchanged and also mass can be exchanged between the surrounding system, there's two variables, both energy and the amount of mass. That is too much for scientific study because we've got two variables and it's not easy to handle. So this kind of system is everywhere. Now we're going to give you an example. What situation? Alright. So example for this kind of system is what? Right? A cup of, let's use coffee. A cup of hot coffee. Just made, right? Right? Without the lid on. Now, without lid on, this is the hot coffee. So if you imagine there's a cup of hot coffee, now that's a cup, right? It's cold. It's cold drink, all right? You don't see anything. But if it's hot tea, what do you see? The steam come out, right? And as soon as the tea is made in the cup, take probably a few seconds, you feel the warmth. You feel the warmth or zip out from the inside of the cup to the outside of the world. This cup is the vessel that you are interested in studying the tea, right? That's the substance. You try to see what the tea can do to the energy. But now you have a energy coming here, but also the steam means what? Steam means the steam of the water brings some hot steam and bring the energy away from the system, right? Go to the surroundings. Not only lose the heat from the wall, also lose the heat from the top, as well as the mass. What is the mass? The water steam, right? Steam is the gas molecule in steam in the gas phase. So you lose the mass, at the same time lose the energy. Too much to study. So we cannot do that. That's an open system. That's a situation. Now, what is the second one? The second system is called isolated. Isolated system. Alright? In first case, open system. Both the energy and the mass can be exchanged between the surroundings and the systems, right? It's too much. Now the isolated system is the opposite. Alright? No energy nor mass can be exchanged between the system and its surroundings, right? You talk about system, then the system has its surroundings, which is outside, at all. Now, if no exchange of mass or energy between the system and surrounding, what can we do to study the exchange or involvement of the substances of our interest inside the system? We cannot do anything because it doesn't exchange, right? It's very difficult for us to do that, but we can do very limited things. So isolated system is not what we normally talk about in this case, right? In this case. So time's almost up. But then our third system, let's put down there. Alright, it's called closed system. Now next part we are continue from the closed system. Time's up. Alright, and what is closed system? Only the